Hello, everyone. This is the supplemental instruction for periodic properties group 7, where I get to just ramble on about stuff. So through the procedure and know what's happening there at physical properties, oxidizing strength, solubility, and relative bond strengths of silver halides. Physical properties will be pretty easy. And if you ever want to look up information, you can also find there's a section in SDS where you can look up the physical characteristics things. Oxidizing strength. This is where we are going to start. So they give a little demo equation right there. And then on the page, they actually work through that demo a little bit with sodium iodine and chlorine. So I think the first thing to do is get a quick review of what an oxidizer is and what a reducer is. Let's see if I can share my screen. Yep. There's always this trippy YouTube lag as I'm live. Nope. Nope. Did I lose that tab? All right. This is currently my favorite one because it has numbers. Yes. So open a new tab. Maybe, yeah. So oxidation is the ability of something to take an electron. Reduction is the ability to lose an electron. So we recently studied these elements over here, and these, when they're in their neutral state, so sodium, just sodium, not sodium plus charge, which we're so used to seeing, these things really like losing electrons because they can't hold on to them. Over here, fluorine we see as the most electronegative element there is. Oxygen's the next, but then you see our trend over here as it goes down. So like this is the strongest thing at taking electrons from other things. And then as the number gets smaller, the ability to take electrons away gets smaller. And so for figuring out what the between oxidation and reduction, I found this. So a lot of terms get thrown out. We have an oxidizing agent, sometimes also called an oxidizer, and a reducing agent, sometimes called a reducer. And we have something that gets reduced and something that is oxidized. And one thing about is these past tense things here means that something acted on them. So if this is reduced, then that means something acted on it. So the oxidizing agent is reduced, meaning it gains electrons. The other common thing is this. This is what I learned in high school, oil rig. Oxidation, loss of electrons. Reduction is gain of electrons. So in their little example up here, the reducing agent gets oxidized. So oxidation is loss of electrons. And the oxidizing agent is reduced. It gains electrons. Now, you don't have to have a perfect understanding of this for this lab, but hopefully this sort of gives you a visual of what's happening. Now, the other thing that we end up looking at is, let's see if I can stop the screen share. Nope, not screen share again, stop it. Is we're going to look at what it means by going through slowly this equation set up right here. And to make it a little, we're actually first just going to get rid of a lot of things. And we're just going to start off by looking at iodine and chlorine. The iodine is coming from the NaI. So this is a solid, it's a salt, and you put it in water. And what happens? It ends up being dissolved. When it dissolves, those two ions like to separate, Na plus I minus. And partly why like to dissolve things that are soluble or like dissolves like, maybe you've heard that before. A big part of it comes down to water. I'm going to draw a little water molecule here. And if you remember, oxygen is one of the most electronegative. It's the only thing stronger is fluorine. So that oxygen really loves electrons. And I'm going to introduce you guys to a new symbol. It's this symbol right here. It means partial. And in calculus, very small increments, but I hate calculus. So this is partial. And what you end up seeing is a lot of people use it to sort of mark the polarity of molecules. So if I put that there, oxygen doesn't have a negative charge. It's just polar. It's slightly more negative on the oxygen side of this molecule. It doesn't have a positive charge. It's just symbolizing the fact that it's a little bit more hydrogen or a little bit more positive on that end of the molecule. And then maybe you've seen symbols like this, where this marks water having a net dipole being like a magnet. So it's a little bit more positive on this end, and it goes to a little bit more negative over there. Anyway, that's important to sort of when you think about like why things dissolve, come up later when we talk about solubility. So sodium, it has a plus charge in water. Well, because it has that plus charge, the oxygen's around it. So plus oxygens and waters. So essentially what ultimately ends up happening is you have this atom of sodium floating around with positive, and these oxygens, they all have negative charges, and opposite charges attract. And those partial negatives actually are what make sodium stable in its ion form as it's floating around in the water. Well, guess what? Iodine has a negative charge. The other end of all these water molecules, see, I can fit an iodine right here, ends up being stabilized by all of the hydrogens on water. Positive. So again, these hydrogens, they do not have a full positive charge. It's just saying that they're a little bit more positive. And all these positives can sort of surround that whole negative charge on the iodine, making it very soluble. So this is the first when you put into water, is it separates into its ions, and the ions are just floating around. Sodium doesn't want electrons. We learned that last time. He's really happy to give them away. So he's not going to interact at all. And that's why in your lab manual, it says that it's a spectator ion. He's floating around. He's like, I don't care about electrons. You guys do your own tug of war. I'm not participating. So to simplify things, we're just going to ignore him for a moment and only write out the guys that are going to be participating. And that gets us to the net ionic equation, essentially. So we don't need that. We have iodine with his negative charge. We have chlorine. And the thing about chlorine is if we look on this periodic table here, iodine's desire for electrons, electronegativity is 2.66. Chlorine is 3.16. It wants electrons more than iodine. And no, that's not what I want. Stop it. Stop screen share. And if we do Lewis dot diagrams, we're going to see that iodine has a full octet because it's in group 7, but it has that negative charge, meaning it has one more electron than it would normally have if it was neutral. So it has a full octet of electrons. This chlorine, it has no charges and there's 2 of them. So how would that end up looking as a Lewis structure? One different color. 1, 2, 3, 4, 5, 7. 1, 2, 3, 4, 5, 6, 7. Chlorine has 7 valence electrons, and you can see why it becomes diatomic is so that it can ultimately share electrons and have 8 total around it. So these 2 in the middle here end up forming the bond that is between the 2 chlorines, making it diatomic. But yet we know that plus electrons more than the iodine. So what happens when things are floating around in solution is a little bit of a mystery. There are ways that they study mechanisms, and a lot of that is way over my head, little what you guys need to know. But one thing that I really like to think about thinking about molecules is nothing happens until they collide. Like they're small and they're flying around in a gas or a liquid or what they're doing, but nothing happens until they collide. And when you're talking about like playing a game of pool or something, it's really easy to get 2 things to collide at the same time, but it's really hard to get 3 things to collide at the same time or 4 things to collide like all at the same time. So just in most cases, just understand like 2 things collide and stuff happens. My notes I had pre-written out. Where's my little stop diagrams? There's what I'm trying to replicate. Okay. So what ultimately happens is chlorine is going to crash into an iodine that's floating around, and it's going to be like, wait, you have an extra electron, I want it more, and it's going to take. So we're going to redraw this and say that this turns into 2 chlorines. For now. Cl 1, 2, 3, 4, 5, 6, 7, 8. Now he has a minus charge. 1, 2, 3, 4, 5, 6, 7. So this isn't a very perfect reaction because I'm leaving off the iodine for a moment. But what you can see here is this guy has an extra electron, and now he's sort of off by himself. Well, what happened to iodine? Taken away. Now he's got 1 less. And this chlorine right here took it. He also got a shot off. Now, this is where, like when you're in solution, lots of different things can happen. You could possibly form a chlorine iodine bond. They'll both have their octet. But just to sort of continue on with this, we're going to actually just say that other chlorine ends up finding another iodine to crash into. So draw him on here. Negative. Here's the other iodine. He's floating around. This guy, he's free. He's a radical right now. He's really pissed off because atoms don't like being radicals. And he's going to crash into this guy. He's going to be like, oh, you've got an extra electron. Yeah. Now we have essentially used 2 iodines to give electrons to our 2 chlorines. And our chlorines now have, I didn't, I'm not going to try that. Have the full octet, got the electrons because they like them better. These 2 iodines up here, they've since been turned into radicals and they've lost an electron. And now, again, I don't know exactly what they end up doing. They could form bonds with a lot of things when they're radicals. But according to what they're saying here happens, is it's going to go to I2. And you can kind of see that now. So since both these two iodines have lost an electron, they're perfectly paired up for trying to share an electron and becoming iodine. So chlorine turned into the ions, and this is turning into a diatomic. All right, put a little bond. And that bond has the 2 electrons in it. That's the Lewis dot diagram, essentially, of what's happening as things collide. And it's these electrons moving to these different compounds that cause oxidation or reduction reaction occur. And the electronegativity chart is a very good thing that says what direction will occur. Now, pointing this out, this is really important for, we're trying to look at trends here. And the trend is one guy is stronger than the other. Well, then obviously the reverse reaction occur. Just look at iodine is able to, or chlorine is able to take electrons away from iodine. Well, that sheet is really covered now. It's important to realize then that the opposite occurs. So say we had an ACl plus iodine diatomic. Chlorine will dissociate from the sodium. Sodium will go do its own thing, and chlorine will become minus. And you know, if chlorine crashes into iodine, he already has his electrons. So let's dissolve this guy first. Na plus, aqueous plus Cl minus. Yes. What are they saying for that too? They're just saying he's floating around. Right too. So that's ultimately what you end up having. Now, when you say like the reaction that's going to occur, at least in organic chemistry, I haven't looked at what they're wanting to put for this rubric. Organic chemistry, let's just say no reaction or something like that, because the reverse reaction is not going to occur. You can also put an X on the arrow, but you need to have some way of indicating that the reverse reaction won't occur. I'll leave everything else up to you guys to figure out, because there's a lot of reactions that we ultimately have to write in this. And you have to be able to balance the reactions. That's essentially the reverse reaction will not occur. So now we're going to get to the solubility of known halide salts. And these questions, and the questions for section will correspond to the questions on the over here, section 3 also. And I think the typo I haven't heard back yet, but on here it's asking bottom left, center, or bottom right. And the problem with that is the fact that these atoms are, these elements are located. So if we do this periodic table, what you'll ultimately see is magnesium is in the top left, zinc is in the center, and lead is in the bottom right. Now the question says bottom left. We're not looking at the elements in the bottom left. So I think that's a typo, but we're comparing top left, middle, and bottom right on the periodic table. These are all chlorine salts. And this part's really easy. You're going to put these in and see how well they dissolve. And I already provided like guiding out to put in things like that. But those are the places that you're looking on the periodic table. Next is the relative strength of silver halide bonds. So what is interesting here is Silver nitrate is incredibly soluble. Well, not incredible, but it's just not a very soluble thing. In fact, it's a rare metal that's often used for money and things like that because it won't dissolve away. If you bury treasure, you would not want your treasure to dissolve. Hence why silver and gold makes really good buried treasure because they don't dissolve over time. Gold's even better. You have to be really mean to gold to get it to dissolve. Chlorine it, you still got to be pretty mean to it, but not nearly as mean as gold to get it to dissolve. We're going to be starting off silver nitrates. AgNO3, right? Yeah. So AgNO3 is what we're starting off with. And we're going to mix all of those with the different halides. But first, I want to look at why perhaps silver nitrate is soluble. There's probably better ways of representing this, but for today, this will work. So silver has a +1 charge. And nitrate is actually a very interesting thing. So I'm going to do NO minus like that. And that's why ultimately it does sort of balance out its charges because we have a negative and a positive. But what ultimately ends up forming this bond is nitrogen here has a set of lone pair electrons. If you look at nitrogen on the periodic table, you'll see that he has 5 valence electrons. And so he has 1, 2, 3. Each of these bonds he's giving 1 electron to. And then 4, 5, these are just sort of sitting off by themselves in a lone pair. And metals, they have their s orbitals, they have p orbitals, they also have d orbitals. And this is where transition metals are actually pretty cool in what they can do to form bonds instead of using like s and p orbitals to form bonds. They'll use their d orbitals, and things like this can just sort of stick their electrons into it. That's called a dative bond. You don't need to know any of this for your course, but that's just sort of how this ends up forming a bond. So what happens is you add O minus. One thing you might realize here is the nitrogen, he only likes to form bonds because, yeah, he likes to form 3 bonds, and he's got 4 bonds right now. And that essentially means that he's got a positive charge. And so the positive from Ag, when those bonds get donated into it, ends up moving over to the nitrogen. It has a positive charge. Now, this molecule, even though it has charges on different parts of the molecule, the overall charge of the molecule is neutral. But we remember when we talked about water having different parts of it that were partial positive and partial negative. That's actually what ends up happening here. In fact, resonance means that this electric, we're not going there. Anyway, negative charge. HO H O H. Go back to polarity though. So if you remember, hydrogen has a partial positive charge. So a bunch of water hydrogens are going to be attracted and they're going to keep it suspended in the water. Oxygen, if you remember, that has a partial negative charge. So oxygens will be attracted to that nitrogen there and help keep it suspended in water. So with these waters being attracted, helping keep it suspended in water, it means that silver nitrate can be soluble. But then we're going to throw in some salts, sodium chloride, sodium iodide. And that's important because we're just going down the periodic table. Chlorine, bromine, iodide. And these things are going to form bonds with the silver instead of nitrate. And so what does that end up looking like? They're going to dissolve and dissociate. And then ultimately, you're going to have Ag, we'll just pick Cl for now. Now, if you remember, silver has a +1 charge. Chlorine, it has a -1 charge when it's an ion. And that's why they're going to end up bonding together. Now, here's the difference between silver chloride and silver nitrate. See how there's no charge necessarily like permanently on this molecule here? Over here, actually. Over here, we had a positive charge and a negative charge, which meant that it had some really good polarity that made it easy to dissolve. That is all gone here. And silver halides, they're not soluble. They're going to precipitate out pretty readily. And so that's the first thing we're doing is we're taking this soluble silver and we're turning into solid silver by reacting it with a halide. And then after I do that, I'm going to do this. Now we get to start testing the halides again because we're not testing halides. This is just going to happen. We're not testing the halides yet. But let's look at what happens when silver forms a bond to ammonia. Ag plus H. There. So here's ammonia, and here's silver. If it was by itself, it would have its plus charge. And again, nitrogen has these lone pair electrons. Those lone pair electrons are on nitrate, also on the ammonia. And those electrons can go into a d orbital. You don't need to know about the d orbitals, but it's just how the bond ends up forming. And what does that mean? Ag H. Again, silver or nitrogen only likes to form 3 bonds, but since we're at 4 bonds here, that nitrogen actually has positive charge on it. Now, positive charge sort of on it, it means that he can be a lot more soluble. Plus, all these hydrogens can have partial positives on them, very similar to water's part positive. And that constant sort of polarity means that it can dissolve in water. And something that's actually, we won't get into why this happens, 2 amines actually end up to the silver somewhere in the lab manual. It sort of hints at that, yeah. Amines. And again, there's a lot of them. And so Ag and H. There we go. And we don't really know where that positive charge has gone, so we put the whole thing in brackets and we just make the whole thing positive. And, you know, might be on this nitrogen, might be on nitrogen. It's just sort of distributed. Take pChem or don't take pChem, but it's on there. And again, since this whole thing has a positive charge on it, means a whole bunch of oxygens will be attracted to it, able to surround it and able to keep it suspended in the water. Now, what this all comes down to is, can that ammonia kick off the halogen? The stronger the silver halogen bond, it's likely it is for ammonia to be able to come in and kick off the halide. And that's what we're going to be looking at for section, what is this, 4? Yep, section 4. We're looking at the can ammonia kick off the halide. If you look at the procedure, there's hints as to, yeah, there's hints. And for that, you need to be able to also write reactions in the end. So that pretty much gets through all of that. What other notes did I have? We covered oxidation and reduction. We covered the silver salts and being soluble and nitrogens donating in partial charges. And we covered those things. So now it's where you get stories, because I think we've covered pretty much everything. You can make chlorine gas at your house pretty easily if you're an idiot high schooler like I was. I don't know. My wife's over there. She probably thinks I was an idiot in high school. We knew each other in high school.
True story.
And chemistry can be dangerous if you don't take the right precautions. And I wanted to remove some rust from the axe head. And I created a solution. You should never mix bleach with anything. Bleach has a lot of chlorine in it. And if you mix bleach acid, it will release that chlorine gas. And I did this in my garage. And it started stinking horribly. So I proceeded to like grab this little bucket that was removing this rust, and I'd have to hold my breath and run and set it down, run away from it, take a breath, run back to the little thing that was cleaning stuff, run further, set it down, run back and take a breath. And I did that until I finally got it into the center front yard. Well, then I felt bad for my neighbors. So I continued that process until I finally got it into the backyard. And what was and horrible is, this is my grassy yard. And this is where I had my bucket of fuming chlorine acid and bleach mix. The breeze was blowing all that chlorine gas. And there was a patch of dead grass, totally burnt brown, that showed up within a day or two afterwards. So the wind was blowing all the chlorine gas this way, and it just burned all bone dry. So please be safe with chlorine gas. We don't want to be sniffing large amounts of it or causing reactions that cause it to be released. Later on in my life, I was working in a prep lab, much like Allie does. She does a fabulous job of keeping all the teaching labs stocked. And I did that at a different university. And it's common to reuse bottles, but you gotta rinse them out enough. Ammonia, it actually comes as ammonium hydroxide. So in the lab, you'll see NH4OH. That is ammonia. If you remove the OH plus one hydrogen, it just turns into water. So when you mix ammonia and water, it turns into hydroxide, but it stinks pretty bad. And there's a caution in there about handle it and don't inhale it. Well, the proper technique for sniffing something is not to stick your nose in a bottle, of course. And I didn't do that. I used proper chemistry techniques. It's called wafting, where you hold a container and you're trying to get a very small scent to see if it is. Well, I wanted to see if this ammonium hydroxide 2.5 liter bottle had been rinsed out or not. So I did that. Or no, it might have been a 4 bottle. I can't remember. But it was plastic, luckily, because even a small waft of pure ammonium hydroxide caused me to drop the empty bottle. And I myself just sort of fell to the floor and landed on my butt and was like, whoa, that was horrible. And I couldn't smell anything for several days. Now, I had perfectly clear nostrils, like everything just got burned and singed out of my face. But I what different smells were for days after a small waft of ammonium hydroxide. So please be careful with the ammonium hydroxide. And another interesting thing related to this lab. I know a professor. He got to Fukushima. There's a typhoon there years ago, and there's a nuclear reactor that ended up melting down. And after all the cleanup and everything was taken care of, there were case studies by international agencies to see like what had happened, what went wrong, what could be done for future nuclear reactors to prevent things like happening. And this professor knows Japanese and was able to go there as he was picked for someone from the United States to go. And before going though, I has a radioactive isotope that gets released from nuclear meltdowns and things like that. And iodine builds up in your thyroid. It's really important for some of the chemistry that your thyroid does. And so one of the problems with people who work with radioactive material or get exposed to radioactive iodine is it ends up going to your thyroid and giving you thyroid cancer. And so just before going to this nuclear reactor to participate in this sort of like group conference thingy, had to like totally max out his thyroid on iodine. So it was taking super high quantities of non-radioactive iodine while in the United States so that he could go and look at a nuclear reactor and not worry about getting thyroid cancer later. I think that's all that I know about the halogens and ammonium hydroxide. Oh, there's one other thing. So in the waste, it talks about separating the two waste streams. We're going to keep the halogens and the organic solvents and the heavy metals in another. I'm actually not sure if we're perfectly doing this because I've been told not using chlorobenzene, we're using water or chlorine bubbled through water and bromine bubbled through water. So waste streams might be different, but relating to the transition metals, we've got lead specifically. Magnesium, it's fairly common, and zinc, it's common enough. But the transition metals on the periodic table, those are the compounds that actually would the ones that I try to be safest with. I've talked about how I don't mind working with acids and bases because most of the time you get little splashes and you quickly learn you've got something on you and you rinse it off and it's reversible damage. Like, oh, I got a burn on my skin. Your skin's fine as long as it's not in your eyes. We wear goggles, that's fine. However, transition metals are very good at causing cancer, essentially, or causing other internal problems. We have lots of chemistry happening in our body that rely on specific metal ions. And if a different metal ion gets into our body, it can kick out the good one and step in instead, which just causes problems. And that's why it's really important for these things not to go down the drain. And water treatment are actually really good at removing all of the transition metals. If you look at that, they have limits on what they're able to remove. They're really good at removing a lot of other stuff, but transition metals, not so much. So when working with these things, please do a good job of making sure that nothing goes down the drain. This lab is not like last week's lab. That's it. If you have questions, let me know or come to office hours Tuesday